Dear students, today we will take up last question in December 19, January 20 question paper. That is question number 10. The 10A, what he asked is, explain the concept of rotating magnetic field and show that resultant flux remains the same at different instants of time. You have to explain with the help of a diagram, vector diagram, then how exactly a rotating magnetic field is producing in a three-phase induction motor. We know that three-phase induction motor consists of three windings of an induction motor. They are displaced by 120 degree that I shown here. There are three windings. Then there is a rotor. Then three windings are excited by a three-phase supply. When a three-phase supply is given, the current in each winding is flowing I1, I2, I3. These are also displaced by 120 degree. When the current is flowing in the conductor, it is producing its own magnetic fluxes. Therefore, there is a flux phi1, phi2, phi3 are producing. Once again, these phi1, phi2, phi3 is also alternating in the nature, and also they are displaced by 120 degree. The same thing is written. Current in winding and magnetic flux produced are also displaced by 120 degree. Then the instantaneous flux produced by the three windings, that is phi1, phi2, phi3 are sinusoidal in nature. Therefore, flux phi1 is given by phi max sin omega t, that is taken as a reference. With respect to this, you have to draw the vector diagram, that is phi1 I drawn. Then you have to draw the what is the flux vector phi2, the phi2 lagging phi1 by 120 degree. That is phi2 is phi2 phi m sin omega t minus 120. It lags phi1 by 120 degree, that you have to draw 120 degree here. This phi1, phi2. Similarly, you can draw the phi3, which is lagging phi2 or phi2 by 120 or phi1 by 240 degree. Therefore, the phi3 is producing here. Then these all three fluxes, they are acting at simultaneously. Therefore, when they are interacting each other, they are producing a resultant flux. The resultant flux is rotating in the air gap, that you have to show. That is the resultant flux produced which rotates in the space. That is phi r is rotating with a synchronous speed in the air gap. How exactly the rotating resultant flux is producing, that we will demonstrate here. Then we know that there are three fluxes, phi1, phi2 and phi3, that is given by phi max sin omega t taken as a reference, phi m sin omega t minus 120, phi m sin omega t minus 240. Our objective is to find out a resultant of these three. If you find out the resultant of any vectors, two or more vectors, then what you have to do is you have to resolve the vectors into its x component and the y components, and you have to take the square root of the x component, y component, that gives the resultant vector. That I am doing here. That is, I have got the three fluxes phi1, phi2, phi3, they are displaced 120 degree. Then I am interested in the horizontal component. That is, what I am doing is I am resolved this phi1, then phi2 is resolved along the x-axis. Similarly, the phi3 is also resolved along the x-axis. You have got here, there is a x component of the phi2 as well as you are getting the x component of phi3 we are getting. Then what is the total horizontal component, what we are getting here is, it is a phi1 is the x component of the phi1 and x component of the phi2 is, this angle is 60 degree. Then if you are taking this triangle, what you are getting is phi2 cos 60. This is phi2 cos 60. Then it is acting exactly opposed to the x-axis plus x-axis. Therefore, I am taking this as a phi2 cos 60. Similarly, the x component of phi3 is also acting here. Then it is exactly opposite to the plus x-axis. Otherwise, it is along the minus x-axis. Therefore, I am writing here minus phi3 cos 60. Therefore, if you are taking the phi1 and you have to substitute the value of the phi1 and phi2, then cos 60 I am taking here as a common phi2 plus phi3. The next step is to you have to substitute what is the value of phi 1, phi 2, phi 3 in this equation. Then after putting this phi 1, phi 2, phi 3 in this equation, after simplification, then the horizontal component of the three vectors what I am getting is 1.5 times phi m sin omega t. Similarly, you have to find out the vertical component of the flux. Then what you have to take is the y component of phi 1, phi 2 and phi 3. Here the y component of phi 1 is 0, then the phi 2, that is the x component of, can see here, it is the y component of the phi 3, then this is y component of phi 2, means phi 2 is acting along the minus y axis and the y component of phi 3 is acting along the plus y axis, whereas the phi 1 is 0. Therefore, you can find out the vertical axis, that is y component of phi 1 is 0, then phi 2 is acting in the minus y axis, therefore it is a minus phi 2 sin 60, and the phi 3, the y component of phi 3 is acting along the plus y axis, therefore it is phi 3 sin 60. Once again sin 60 you can take common here, then if you are writing phi 3 minus phi 2 into sin 60, then once again you have to substitute the value of what is the value of phi 2 and phi 3 in this, and you have to apply the sin a plus b form or cos a plus b, sin a plus b form. Then you have to simplify, then the vertical component what I am getting is 1.5 phi m cos omega t. What I am interested here is the resultant flux, therefore you have to take the addition of square of phi h and phi v, and you have to take the square root to get the resultant. Therefore phi h, phi v, then if you are vectorially adding these two, then what I am getting is the resultant. This resultant how we are getting is here under square root phi h square plus phi v square, then you put the value of phi h and phi s square and you have to take, because sin square omega t plus cos square omega t you are getting in the bracket, that is equal to 1, the ultimately what we are getting is 1.5 times phi m. That is the resultant vector what I am getting here is 1.5 times the phi m. Then what is the angle made by the resultant with respect to reference? That we have to get it from tan theta is equal to phi v by phi h. What is the phi v? Phi is 1.5 cos omega t, phi h is 1.5 phi sin omega t. Here 1.5 m, 1.5 phi max is get cancelled, cos by sin you are getting, that is cot, that cot can be converted into a tan, then what you are getting here is, that is cot omega t you are getting, cot omega t is converted into tan 90 minus omega t, both sides we have got a tan function, therefore theta is equal to 90 minus omega t. That is resultant is making theta with respect to reference is given by 90 minus omega t. You have to take these two and you have to see that how there is a rotating magnetic field is producing here. Then you are getting a theta is equal to 90 minus omega t, phi r is equal to 1.5 m. Then you have to consider at a different instant of time. When omega t is equal to 0, what is the resultant flux? Resultant making an angle of theta is equal to 90. Then what is the resultant flux? That is 1.5. This is 0 axis, that is 0 degree. Then theta is equal to 90, that you have to take it as a positive value here, because it is plus 90, that is you have to take in the anti-clockwise direction. This phi r is 1.5 m. The next case I am considering here, omega t is equal to 90. Here omega t is equal to 90, if you are substituting 90 here, theta is equal to 0, means resultant vector is all along this axis with the same magnitude because it is independent of time. The next case what I am considering here is omega t is equal to 180. If you are putting 180, theta what I am getting is 90. 90 means what? With respect to reference, it is making an angle of lagging angle 90. Here it is 1.5. Previously it is at this position, then it is moving to the B position. Now it is moving from B to C. Now further I am taking omega t is equal to 270, then what I am getting is theta is equal to 180 degree. Therefore, what I am getting is theta is equal to 1.5. That is, it is moving from point C to D. Now the cycle repeats. Means the continuously the rotating flux is producing here with the same magnitude of 1.5 m. This is how we have to explain the rotating magnetic field is producing in a three-phase induction motor when a three-phase supply is given to the stator winding. Now the question number 10b, what he asked is a numerical on the alternator is given a three-phase 50 Hz 20 full silent pole alternator with a star connected stator winding, has 180 slots on the stator. There are 8 conductors per slot and the coils are full pitched. Therefore, you have to take Kc and Kd is equal to 1. The flux per pole is 25 milliweber. Assuming sinusoidally distributed flux, calculate speed, generated EMF for phase and the line EMF. That is phase voltage, line voltage and the speed he asked. Just you have to note down what are the given data. That is, a P is given 20, phi is 25 milliweber. It is star connected. Frequency is given 50 Hz, 180 slots with 8 conductors per slot, and the Kc and Kd is equal to 1. Therefore, Kw is equal to 1 he is given. Then what is asked is speed per phase voltage, line voltage. The first step is to find out the total number of conductors here from the given data. How to find out the total number of conductors? Number of slots multiplied by number of conductors per slot. Therefore, it is 180 into 8, 1440 is the number of conductors. What you are interested is, we are calculating per phase voltage. Therefore, what I am interested is per phase the number of conductors. This 1440 is meant for the three phase. I want per phase the number of conductors. What you have to do is Z divided by 3 you have to make it. Therefore, what I am getting is 480. In the equation I have got a TP. You have to convert ZP into ATP. The number of turns per phase is equal to ZP by 2. Therefore, it is 480 divided by 2. That is what I am getting is 240. Then we can straight away you have to apply the EMF equation here. That is, the speed you can calculate. Speed is equal to 120 F by P. F is given, P is given. Therefore, you can calculate the speed N is equal to 300 RPM. Then the phase voltage you have to calculate first. Then you have to find out the line voltage. The equation for the phase voltage is 4.44 Kc Kd phi F Tp Hz. All the data is given. Kc and Kd, that is nothing but Kw, that is what is given is 1. Phi is given 25 milliweber. F is 50 Hz. Tp already we are calculated 240. Just you have to substitute. You have to get the per phase voltage is 1332 volts. Then you have to find out the line voltage by multiplying root 3 to the phase voltage because it is star connected. Therefore, what I am getting here is EL is equal to root 3, 1332. Therefore, the line voltage of an alternator, what you are getting is 2307.09 volts. This is it is simple numericals. First, only to find out the total number of conductors per phase, turns per phase. Then you have to apply the voltage equation 4.44 Kc Kd phi F Tp volts. All the data are given. Just have to substitute and find out the phase voltage and the line voltage. The question number 10c, what he asked is describe the construction features of synchronous generator with suitable diagram. You have to explain the two important parts of the alternator. One is the stator and the rotor. Therefore, the basic parts of a synchronous generator consist of a rotor. In the case of the alternator, the rotor is nothing but it is a field system, that is a DC excited winding. It is a field system, where in the case of the alternator, the stator is nothing but a armature. It is consists of three-phase winding in which the AC EMF is generated. Then you have to write about the stator. It is a stationary part of the machine. The various part of the stator includes the stator frame to hold the stator assembly, stator core to accommodate the armature windings, that is stator windings, and cooling arrangement. They are making the ventilating ducts are provided in the stampings of the stator. In order to reduce the hysteresis and eddy current losses, usually the stator and the rotor, they are made up of laminations with a high grade silicon content steel laminations. Then in the stator, in its inner periphery, they have got a slot in which they are placing the armature, the winding in which there is a induced voltage. These three-phase windings usually connected in star and neutral is grounded. It is about the stator. Then we have got a rotor. It is a rotating part. It is called magnetic field structure carrying the DC exciting winding. In the case of the alternator, there are two types of the rotor you have got. One is called as a salient pole. It is also called as a projecting type. You can see here it is a poles are projected here, and the air gap is not uniform throughout. In the case of this type of alternator, the rotor which has got the salient pole or a projecting type, in that case the air gap is not uniform. This is one type of alternator, then it is called as salient pole type of alternator. Then for that you have to draw this diagram and you have to name the different parts of the alternator. One is the salient pole alternator. The another one is the non-salient pole, also it is called as a cylindrical rotor. That is, you can see here the air gap is uniform throughout here. Then here the poles are not projected. It is looks like a cylinder, therefore it is called as a cylindrical type of the alternator. Cylindrical type of the alternator. This is how we have to explain the construction of the alternator, drawing the two diagrams, one for a salient pole, the other one is for a non-salient pole, and briefly you have to explain what you mean by the stator, what is the function of the stator, and what is the function of the rotor. This is how you have to attempt the questions. Draw the neat diagrams, write the correct theory for each the theory questions, and the problem just you have to note down the data and solve the numericals using the appropriate formula. Good luck.